So question 1, we're expanding these two terms, so we're going to focus on the one with the power first. You need to make sure that there is a 1 here for us to be able to use the expansion formula. So we're going to focus on this. And we get 1 plus 1/2 times, and remember our term here is negative 2x, plus 1/2 times negative 1/2, because that's 1 take away 1. Sorry, 1/2 take away 1 over 2. 2 factorial is obviously just 2. And then we're squaring negative 2x. Be careful to put the brackets around here because we know we're squaring both of these two. So that gives us 1 minus x minus 1 over 8, 4x squared, which is just 1 minus x squared over 2. So then we're going to multiply that expression by the other part. So it's 3 plus x. And they actually want all of the terms up to and including x squared. So you need, whilst in some questions they just focus on one term, here they want all of them. But you only need the ones up to and including x squared. So the order you do this expansion is up to you. So I'm going to focus on the 3. So I'm going to multiply everything by 3 first. So it's 3 minus 3x minus 3x squared over 2. Then I'm going to multiply everything by x. That's plus x minus x squared. And as I said, I can stop here because I know that x times the negative x squared over 2 gives me an x cubed term. So now we just need to join like terms. So we get 3 minus 2x minus 5x squared over 2. So question 2, you can see here you've got 2 log statements and then just a coefficient. So ideally we want to have them all as a log statement. So I'm going to rewrite my 7 as with the same log. So we've got ln x minus 5 equals 7 ln e, because we know ln e is just 1. So we've got minus ln x. There's probably several different ways of doing this. This is the way I'm choosing to do it. So ln x minus 5. I can bring my, using index laws, or log rules, I can bring my 7 up here. So I've got ln e to the 7. And now because I have 2 log statements, I can combine those as well. So I've got ln x minus 5 is equal to ln of e to the 7 over x. Because I have 2 log statements, I can then just remove the log. So I've got then x minus 5 is equal to e to the 7 over x. Rearranging that, I have x squared minus 5x equals e to the 7. And then x squared minus 5x minus e to the 7 equals 0. So I'm then going to solve that using the quadratic formula. So I've got x equals positive 5 plus or minus the square root of 5 squared. I guess that should be negative 5 squared minus 4 times 1 times negative e to the 7 over 2 times 1. Obviously you can put this in your calculator. You will get the 2 values of x1 is 35.70968 and x2 is negative 30.70968. As we know, x cannot be a negative value in this instance because we've got log statements, and so our answer or solution here is 35.71. First step here, if we want to write this as a straight line, we're going to take logs of both sides. So we've got ln a to the y is equal to ln bx. Y can come in front, laws of logs. And I can separate these two into ln b plus ln x. I then can say that y is equal to ln b over ln a plus ln x over ln a. I know that our gradient is represented by the value in front of ln x. So our gradient is going to be 1 over ln a. I can now find our gradient because I have two coordinates. So m is equal to change in y over change in x. Which is 250 over 487. Which means that 1 over ln a is equal to 250 over 487. So, ln a is equal to 487 over 250. That means that a is equal to e to the power of that. So the value of a is 7.0146. So in this case, to the nearest integer would be 7. To find b, I'm then going to substitute in values for one of the coordinates. So it's probably easier to have this as a decimal value at this point for the substitution purpose. So it's 1.948 to a few decimal places. So I'm going to focus on that first coordinate, the 0.336, 1.00. So I'm going to substitute those values in. So I've got 1 is equal to ln b over 1.948 plus 0.336 over 1.948, which gets me 403 over 487 is equal to ln b over 1.948, which means ln b is 403 over 250. Oops, I'm running out of space. So e to that power 4 over 3 over 250 gives me 5.01. So which gives me b, sorry. So b is 5. So there's our two solutions. So number 4. So I'm going to start off finding r. So r is the square root of our two coefficients here, or our two values here. So it's -1 squared plus -√3 squared, which is 1 plus 3. So square root of 4, which is 2. So r is 2. Tan theta is then, I tend to just focus on the values rather than the sign, so it's root 3 over 1. So that works as theta is pi over 3. Now, if we look at the Argand diagram here, this is where our vector would be positioned, which means that this angle here is your pi over 3. But as we know, we're looking for this angle here. So that's going to, and we know it's going to be negative. So we're going to do pi take away pi over 3, which is 2 pi over 3. And as I said, we know therefore it's negative because it's down below. So writing in that format, we've got 2 cos negative 2 pi over 3 plus I sine negative 2 pi over 3. So the complex number v is equal to 5 brackets cos pi over 6 plus I sine pi over 6. So the value for r in this, for v, we can see is 5. The value of r for u from up above we know is 2. So that means the value of r we're looking for in this instance is going to be 5 over 2 because it's v over u. So we have our value for r. We now need to find our value for theta. So theta, when we have complex numbers where they're divided, we would subtract our values for theta. So our theta here is pi over 6. So pi over 6, and we're taking away our value for theta above here, which was negative 2 pi over 3, which gives us 5 pi over 6. So in the format they've asked us, it would be 5 over 2 e to the I 5 pi over 6. Question 5. So we've been given the equation of a curve. We're trying to find dy dx and then find the x coordinates of the stationary points. Well, hopefully you'll recall that the stationary points occur when dy dx is equal to 0. So we're finding the derivative. We can see we've got one term divided by another, so we're going to use the quotient rule. So in this instance, I've got u is equal to e sine x, which means du dx is going to be cos x e to the sine x using the chain rule. V is cos squared x, which I'm just going to help myself out by reminding myself that that means cos x all squared. dv dx is then going to be, again, using the chain rule. So we've got 2 cos x, removing the power, but then remember we multiply by the derivative of cos, which is minus sine x. So let's use our quotient rule. So dy dx is cos squared x cos x e to the sine x minus, but we're taking away a negative, therefore I can change this to a plus, 2 e to the sine x cos x sine x. Obviously we're multiplying these, so the order isn't important. It's not the way I've worked out here. I've just written in something that looks a little bit neater. Over cos squared x all squared would then be cos to the 4x. Okay, so there is our derivative. As we said, to find the stationary points, we know that that derivative is equal to 0. So 0 is equal to cos cubed x e to the sine x plus 2e to the sine x cos x sine x over cos 4x. So when we rearrange this to find 1, 0, we bring the cos 4x up here, which means that disappears, becomes 0. So we're trying to then find 0 is equal to cos cubed x e to the sine x plus 2e to the sine x cos x sine x. I can factorize here, so I can bring e to the sine x and cos x out here, which leaves me with cos squared x plus 2 sine x. I know that this cannot equal 0 because we've got e to the power of something. So I'm going to focus on this bracket. I've got a combination of cos squareds and sines, so I'm going to use one of my identities here and know that cos squared is equal to 1 minus sine squared. And I'm trying to solve when that is equal to 0. I always prefer to have the sine squared x as positive, so I've got sine squared x minus 2 sine x minus 1 is equal to 0. Using the quadratic formula, I would then say that sine x is equal to positive 2 plus or minus the square root of negative 2 squared minus 4 1 lots of minus 1 over 2 lots of 1. So I then get that sine x is equal to 2.142, which we know is impossible because the maximum value is 1. Or the alternate is sine x is equal to negative 0.414213, which gives me a value of x is equal to negative 0.427077. Remember, we're working in radians here. We need to find any alternate solutions. Especially given that this is not in the range specified in the question. So up here, they've said between 0 and 2 pi. Again, how you do this is up to you. I like to sketch my sine graph. Oh gosh, it's not great. So the value I found is just here. My values I'm looking for are over here. So I know that this value is representing 0.427, which means that this value here would also represent 0.427, as does this one. So my values I'm looking for are pi plus 0.427 and 2 pi minus 0.427. Let me just double check on the rounding. They haven't specified, so let's do 3 significant figures. So 3.57 and 5.86. Okay, number 6. So by sketching a suitable graph, show that the equation cosec 1 x over 2 is equal to e to the x minus 3 has exactly one root. Okay, we've been asked to sketch unfamiliar graphs. The easiest way is to set up a table of values and plot a few points, or at least have an idea of where your graphs are going to be situated. So we're going to choose some values of x. 0 is normally a good one. Its terms, its cosec, which we know is 1 over sine. So I might actually use multiples of pi. Maybe I'll do pi over 3, pi over 2, maybe 2 pi over 3 and pi. So I'm finding sine of, 1 over sine. So sine of 0 we know is 0, so 1 divided by 0 is undefined. So then we're going to, sorry, just change my settings on my calculator to radians. Okay, so 1 over sine pi over 3 over 2 gives us 2. 1 over pi over 2 is root 2. Pi over 3 is 2 root 3 over 3, and pi is 1. So that's going to give us a good idea of what that one looks like. Then we're finding e to the x minus 3 for those same values. So e to the power of 0 minus 3 is minus 2. Pi over 3. It's negative 0.15. So it's 1.81. .12 and 20.1. Okay, so then we want to try and draw a set of axes as accurately as we can. So we've got 0, pi over 3, 2 pi over 3, and pi. I might just plot those ones. So our first one is pi over 3 is at 2. That's 1, 2, minus 1, minus 2. 2 pi over 3 is 2 root 3 over 3. Helpful to have that as a decimal number. .15 and pi So we know our graph, this one is going to come down like this. And then we've got -2 for the, oh, maybe I do a different colour. -2 so for this one. -0.15, so it's perhaps about here. 1.18. Oh, that's for that one I wasn't going to bother with. 5.12, so that's going to be way up here. And that one's way out of the range. Okay, so as we can see, it has exactly just one root. They cut each other just once. Verify by calculation that the values lies between 1 and 2. Couple of different ways of doing this. You can substitute in these two values and compare your outputs, or you can move everything to the same side and determine if one goes from negative to positive. I'm going to substitute the values in. So when x equals 1, cosec x over 2 is equal to 2.08. When e to the x minus 3, it's negative 0.28. So I can see that this value is greater than this value. So 2.08 is greater than negative 0.28. When x is equal to 2, I've got cosec x over 2 gives me a value of 1.188. And e to the x minus 3, our value is 4.389. And here we can see that our cosec value is less than our e to the x value. So the limits between these values. So if we want to show that a sequence of values in the interval of this converges, and it converges to alpha. So essentially all we want to do here is to rearrange this iterative formula to get to the original, or vice versa. You can start with the original and end up with this expression here. So first things first, I'm going to drop the n plus 1 and n. So I've got x is equal to ln cosec x over 2 plus 3. Because I've got natural log, I can rewrite this statement as e to the x is equal to cosec x over 2 plus 3. And then I'm just going to subtract 3 from both sides, which is what I started off with. So now we're being asked to use the iterative formula with our initial value of 1.4. So our first value is 1.4, so we're going to substitute that in to get our second value. So it's ln cosec 1.4 over 2 plus 3. And we're writing each of these to 4 decimal places. So x3 is going to be ln cosec 1.5156 over 2 plus 3, 4940. Now it would be useful at this point, so once you've entered your original calculation, to actually change this portion on your calculator to use the ANS, or the answer key, the answer button. And that means you can just keep pressing execute or enter to find your next value in the iterative sequence. So we get 1.4978. Our next value is then 1.4971, 1.49 7, 2. Remember, we're trying to establish our value correct 2 decimal places. So we then look at each of these correct 2 decimal places. So this would be 1.52. This would be 1.49. This would be 1.50. This would be 1.50. And this would be 1.50. So we can see that all three of these gives us the same final solution of x is equal to 1.50. We could have actually stopped at this point, having had two the same. So state the minimum number of calculated iterations needed. So as we said, we needed this one, this one, this one, and this one. We could have stopped there. So that would be, our value here would be 4. Number 7, we're looking at the Argand diagram. So these two separate things, we want to identify what they look like. So, modulus z minus I'm going to rewrite this as 3 minus 2i would equal to 2 would be a circle center 3 negative 2 radius of 2. If I had w minus, again I'm going to write it like this, is equal to w, I'm going to write minus negative 3 plus 4. We're looking for the perpendicular bisector of the 2 points. So these 2 points we're looking at are 3, negative 2 and negative 3, 4. So first of all, I'm going to find the midpoint of those coordinates. So it would be 3 plus negative 3 over 2, negative 2 plus 4 over 2. So that would be 0, 1. And then the gradient of those two coordinates, I don't know if you'd bracket, 4 minus minus 2 over negative 3 minus 3, which would be 6 over negative 6, which is negative 1. So the perpendicular gradient would be 1. So that's just going to enable me to do a decent sketch. Oh, I've used most of my space already. So I am going to draw my set of axes. I need to show my circle of 3, negative 2, radius 2, This is going to hit there. Gosh, it's terrible. And then this goes through 0, 1. Let's try and keep my scale quite decent. 1, 2. And then it would have a gradient of 1. There we go. Okay. I could put the other point in, I guess. Minus 3. 1, 2, 3, 4. That's the other point up there. Okay. Hence, find the least value of z minus w for the points on these loci. So if we're trying to find the least value, what we're essentially doing is finding the distance between the loci. So in other words, the measurement between the circle and the midpoint, or the coordinate 0, 1. So in other words, this measurement here. So what we can do here is to imagine that the line is going all the way to our center of our circle from this point, and we can form ourselves a right angled triangle. So if this point is our center of 3, -2, then our horizontal measurement would be 2. Oh, I'm so sorry, 3. And our vertical measurement would be 3. So we've got this distance here would be 3 squared plus 3 squared, which is root 18. And then, so that's the distance from this coordinate right the way through to the center. And then this measurement is going to be that distance subtract the radius of our circle. So in other words, we're looking at a measurement of root 18 take away 2. So number 8, we've been asked to use substitution to find this integral. So we know that u is equal to 1 minus sine x. Often helpful to rearrange this at some point, but let's start with differentiating it. So du dx is equal to minus cos x. So we can get an expression for dx, so that's -1 over cos x du is equal to dx. We're going to need to replace our values for x. So when x is 3 over 2 pi, u is 1 minus sine of 3 pi over 2, which works out to be 2. So it's our u1, and 1 minus sine pi gives us a value of 1. So our new limits are going to be 2 and 1. I'm also going to replace the sine 2x using the identity sine 2x is equal to 2 sine x cos x. So let's put that stuff in now. So we've got 2 sine x cos x on the top over the square root of 1 minus sine x, we know it's u. Then dx is -1 over cos x du. So we can see our cos x cancel. We now need to rewrite the sine x in terms of u. So let's go back to our original substitution. So an expression for sine x would be 1 minus u. Right, so now I can replace everything. So I've got 2 lots of 1 minus u over, and I'm going to write this, -2, because of this negative here. And that's u to the half to u. At this point, we could always bring the -2 to the front, so let's do that. It's probably going to make lives easier. So 2, 1, and I'm going to separate my terms to 1 over u to the minus half minus u over u to the half, which gives me -2 to 1 u to the -1/2 obviously it's a power of 1 minus u to the half du. So I now need to integrate. So that's u to the half over half minus u to the 3 over 2 over 3 over 2. And we need an exact value here, so minus 2. So we've got 2 lots of 2 to the half. Well, maybe I should rewrite this. Negative 2. So that's u to the half divided by a half is 2u to the half minus 2u to 3 over 2 over 3. Okay, minus, so that's, 2 cubed, apologies, 2 brackets 2 root 2 cubed over 3 minus 2 1 to the half minus 1. Oh no, it's 2. Whoops. 2 1 to 3 over 2 over 3. So we've got 2 root 2 minus so it's 4 root 2 over 3. So it's just going to be minus 2 minus 2/3. So we've got 2 root 2 minus 4 root 2 over 3. Two minus 2/3 minus 4 over 3. So that gives us minus 4 root 2 over 3 plus 8 over 3. Let's just double check. A plus b root 2, where a and b are rational numbers. So we have that there. So question 9. If the lines L1 and L2 are perpendicular, we're going to focus on the directional vectors, and we would find that the scalar product of those would be 0 if they're perpendicular. So that means we've got 2 multiplied by 3 plus negative 1 multiplied by negative 2 plus a multiplied by negative 2 would equal 0. 6 plus 2 2 minus 2a is equal to 0. So 8 is equal to 2a, and a is equal to 4. So there we go, we have shown that a is equal to 4. Here they've told us that the lines do intersect. So we need to write parametric equations here for each of the two, line 1 and line 2. And if they meet, which the question states that they do, then those I and j and k equations would be equal to each other. So I would see that 1 plus 2 lambda would equal negative 1 plus 3 mu. Negative 2 minus lambda would be equal to negative 1 minus 2 mu. And 3 plus 4 lambda is equal to negative 1 minus 2 mu. Let's rearrange these a little to make it look a bit nicer. So that's 2 is equal to negative 2 plus 3. Negative 1 is that. And 4 is equal to negative 4. So I've then got 3 equations. So essentially what I need to do is to solve simultaneously. So I'm going to look at equation 2 and I'm going to add it to equation 3 to start with. So that means, actually no, I want to subtract, apologies, because I've got both of them are negative 2, so I want to subtract. So I've got negative 5 is equal to 5 lambda, which means lambda is equal to negative 1. Let's just check that that gives me the same value when I bring in equation 1. So what I'll do is I'll have 2 lots of equation 1, and I'm going to add that to 3 lots of equation 3. So 2 lots of equation 1 is 4 is equal to minus 4 lambda plus 6. 3 lots of 3 is 12 is equal to minus 12 plus, minus 6. And we're adding those. So it's going to get me 16 is equal to negative 16. And once again, lambda is equal to negative 1. So we have managed to establish that for all 3 of those equations, the value of lambda is negative 1. We would then substitute that back into our parametric equations to find our point of intersection. So we would have 1 plus 2 lots of negative 1, negative 2 minus negative 1, and 3 plus 4 lots of negative 1 as our point, which is negative I minus j minus k. Part C, the point A has position vector negative 5i plus j minus 9k. Show that it lies on L1. So looking at L1, that's r is equal to I minus 2j plus 3k plus lambda 2i minus j plus 4k. So if it does lie on there, then we should find that we would have the same value of lambda for each of the parametric equations. So 1 plus 2 lambda would equal negative 5. Minus 2 minus lambda would equal 1. And 3 plus 4 lambda would equal negative 9. So let's solve each of these. So that gives me 2 lambda is equal to negative 6, so lambda is negative 3. Here we've got negative lambda is equal to 3, so lambda is negative 3, is looking good, and 4 lambda would be equal to negative 12, so there we go. Sense is the same value for each A does lie on L1. So our final part D. The point B is the image of A after reflection. So from above, the point A is, this is just a visual representation, negative 5, 1, negative 9. So that's point A. We know that point A lies on line L1. So L1 would be heading this way. We also know that if it's a reflection in the line L2, so if this was L2, then point B would be of equal distance from that mirror line. So this would be point B. And this point here would be the midpoint. And we know that line 1 and line 2 meet at the point negative 1, negative 1, negative 1. That's what was found in part B. So I'm going to call this A, B, C as a general point. So I know that negative 5 plus A divided by 2 would give me negative 1. 1 plus B over 2 would also be negative 1. And negative 9 plus C over 2 would again be negative 1. So I need to solve all of these. So negative 5 plus A is negative 2. So A is 3. 1 plus B is equal to negative 2. So B is negative 3. And negative 9 plus C is equal to negative 2. So C is 7, which gives me the position vector of B as 3i minus 3j plus 7k. Question 10, part A. So we're given that 2x is equal to tan y. We need to show that the derivative is 2 over 1 plus 4x squared. So let's differentiate. So we've got 2 is equal to, so the derivative of tan is sec squared y, but because it's y, it's dy dx. We know that sec squared is equal to 1 plus tan squared from the identity. So then we've got 2 is equal to 1 plus tan squared dy dx. So 2 over 1 plus tan squared y is dy dx. Now we notice that everything here is in terms of x. So going back to the original statement that 2x is tan y, which says that tan squared y would be 2x all squared, which is 4x squared. And so let's just go and do that final replacement. So dy dx is 2 over 1 plus 4x squared. So part B, just warning you, there's 7 marks and it's not a nice one. So we've got x tan to the minus 1 of 2x. Now we're actually going to use integration by parts here. I'm going to call u tan to the minus 1 2x. that enables us to differentiate. If you remember up above, we were given 2x is equal to tan y, and we showed that dy dx was 2 over 1 plus 4x squared. So rearranging this would be y is equal to tan to the minus 1 of 2x. So if I've called u tan to the minus 1 of 2x, that means that du dx is going to be 2 over 1 plus 4x squared. With integration by parts, our other part x, so that's going to represent dv dx, which means that v would be x squared over 2. So I'm now going to use the integration by parts formula. So as we may or may not recall, that would give me uv. So we've got x squared over 2 tan to the minus 1 2x minus the integral of x squared over 2 multiplied by 2 over 1 plus 4x squared dx. Now, good thing is that our 2's cancel, but this still ends up as x squared over 1 plus 4x squared dx. So we need to integrate this part. Because we have an x squared on the top and also on the bottom, we need to separate these, which means we need to sort out use partial fractions. Since the power of the x squared is the power of the x is the same top and bottom, we first of all need to do a long division. So we've got x squared being divided by 4x squared plus 1. It's just easier to write it that way. So x squared divided by 4x squared is 1/4. So that gives us x squared plus 1/4. And we subtract these to get negative 1/4. So splitting this part here into partial fractions, we've got 1/4 minus 1 over 4, 1 plus 4x squared. So, oh, apologies. I don't know why I wrote 1/2. It's 1/4. So we now need to integrate both of these. So let's rewrite this here. Actually, what I'm going to do is bring my quarter to the front. So I've got 1 minus 1 over 1 plus 4x squared dx. So we want to rewrite this with just x squared. So this is going to become, bring the 4 out, and we've got x squared plus 1/4. And so that is equivalent of 1 over 4 x squared plus 1/2 squared dx. So using this from the formula booklet, we've got 1/4 x minus 1/4, so I'm taking that quarter out, and then I'm going to have 1 over 1/2 tan to the minus 1 of x over 1/2. So that's 1/4 x minus. So 1 divided by 1/2 is 2, so that's going to be 1/2 tan to the minus 1. Again, that's going to become 2x. So now I have to put all of that back into this step here. So we've got x squared over 2 tan to the minus 1 of 2x minus, so we're taking away all of this integral that we just found. So we've got minus x over 4 now plus 1 over 8 tan to the minus 1 of 2x. And then they are all with those limits of 3 pi over 2 and I think it's 1/2. So we now need to input those values. So oh, sorry, this is not 3 pi over 2, it's root 3 over 2. So our final part to this question is to substitute in our limits. So we've got root 3 over 2 squared divided by 2 tan to the minus 1 of root 3 minus root 3 over 2 divided by 4 plus 1/8 tan to the minus 1 root 3. Take away 1/2 squared over 2 tan to the minus 1 of 1 minus 1/2 over 4 minus 1/8 tan to the minus 1 of 1. So, because they want an exact value, we have to keep this as accurate as possible. So, root 3 over 2 squared divided by 2 is 3 over 8 tan to minus 1 of root 3 is pi over 3 minus root 3 divided by 2 divided by 4 is root 3 over 8 plus 1/8 pi over 3. Take away 1/2 squared divided by 2 is 1/8 tan to minus 1 of 1 is pi over 4 minus 1/2 divided by 4 is 1/8 minus 1/8 pi over 4. So we've got pi over 3 minus root 3 over 8 minus pi over 32 oh, this isn't minus, this is plus. Pi over 32 minus 1/8 plus pi over 32. So, pi over 3 plus pi over 24 is 3 pi over 8 minus root 3 over 8. So pi over 32 plus pi over 32 is pi over 16. So it's minus pi over 16 plus 1/8. So we've got 3 pi over 8 minus pi over 16 is 5 pi over 16 minus root 3 over 8 plus 1/8. And since they want the exact answer, that's as simple as it should go. So question 11 is the final question. In a field there's 300 plants, all of which can be infected by a disease. At the time t, after the first plant is infected, there are x infected plants. The rate of change of x is proportional. Okay, so here we go, start writing stuff. So the rate of change of x would be dx dt is proportional to the product of the number of plants and the number of plants that are not infected. So if the number of plants infected is x, that means that there would be 300 minus x who are not infected. Using normal rules of proportion, we would replace the proportionality sign with an equals k. And we now need to find k. So we know that when dx dt is 0.2, the value of x is 1. So that's 1 times 299. So k is 0.2 divided by 299, which is 1 over 495. So that means that dx dt is equal to 1 over 495 x 300 minus x. So all we need to do now is to just rearrange that. Apologies, this is 1495. We just need to rearrange that so it looks as it does in the original question. So we're going to multiply both sides by 1495. So 1495 dx dt is equal to x 300 minus x. So part B. So using partial fractions, solve the differential equation. So we've got, let's focus on the 1 over x. Apologies, let's. First things first, we're going to separate the variables. So we get integral of 1 over x 300 minus x dx on one side is equal to integral of 1 over 1495 dt on the other. So I'm going to use partial fractions here. So I've got 1 over x 300 minus x is equal to a over x plus b over 300 minus x. So 1 is equal to a 300 minus x plus bx. If I let x equal 300, then 1 is equal to 300b. So b is 1 over 300 and x equals 0. So 1 equals 300a. So a is also 1 over 300. So I've got 1 over 300 integral 1 over x plus 1 over 300 minus x dx is equal to 1 over 1495 dt. So I've got 1 over 300, so let's integrate. So 1 over x, that would be ln x. And then this is going to be plus ln 300 minus x divided by -1. And this is going to be equal to 1 over 1495 t plus c. So I'm going to bring the 1495 over to here. So then I've got 1495 ln x minus ln 300 minus x is equal to t actually, let's put the plus c here. We know that when t is 0, x is 1. So we've got 1495 over 300 ln 1 minus ln 299 plus c equals 0. We know that ln 1 is 0. So we've got c is equal to 1495 over 300 ln 299. So then we've got an equation of t is equal to 1495 over 300 ln x minus 1495 over 300 ln 300 minus x plus 1495 over 300 ln 299. Well, as you can see, we've got 1495 over 300 that's common here. Ln x plus, so we've got ln 299 times x over 300 minus x. So that's combining using our log laws. And then we'll simplify that to 299 over 60 ln 299x over 300 minus x.